Thank you, Richard. Great, thank you. So, as I am new, I thought I'd start with a quick introduction to me. I look around the room and I'm surprised I don't know many people at all, which was probably a good thing. So I have a PhD in material science, which I got at Macquarie Uni, green symbol at the top. From there I went to ANU and I worked in electronic materials engineering in 3.5 semiconductor deposition by metal organic chemical vapor deposition for applications in high-speed communications and in optoelectronics. From there I went to Sydney Uni for a year and a half to the Optical Fibre Technology Centre, where I worked on semiconductor doped optical fibres for applications in photonics. And from there I joined Pacific Solar, which was a spin-off of the University of New South Wales. I joined that company to be the silicon materials device deposition expert, and I did the CVD, chemical vapor deposition of silicon for Pacific Solar. I stayed with Pacific Solar when they became CSG Solar, and we took the technology into manufacturing in Germany. At that point I was pilot line manager and responsible for technology transfer. Ultimately, when we went to Germany, Paul Bazor was CTO. When he left, I became CTO of CSG Solar. Then there was a transition from CSG Solar when Suntech actually invested in the technology to begin with, and then ultimately bought the Australian R&D group and named it Suntech R&D Australia, which I was the managing director for 4 or 5 years, and that's recently been wound up, the Suntech R&D Australia activity. Suntech is still active in Australia in its commercial enterprises, but it no longer has an R&D group here. It has withdrawn all its R&D back to China and has a direct relationship here with the university rather than through a private company. And about a month ago, I was recruited to join the University of New South Wales as the node leader of this activity. I'm also the chair of the Australian PV Institute, so it's been a busy last month with the various activities. I've been trying to come up to speed with what's happening at UNSW. I hope that I can do justice to the work that's been done here in the last year and the plans for the next year. I have the diversity of the work here at the university is really impressive, and I'm not across it all yet. Not surprising, I probably won't be in a year's time, but I'll give an overview presentation at this stage, and I will rely on the presentations from the 3 of the members of staff here and the students in 8 posters in the next couple of days, so that you get a more depth from what's happening here. So I won't go into much detail, but one of the strengths of the work that comes from the University of New South Wales is the long history. We heard a fair bit about that in the last couple of days, based on the 40 years of activity here. Much of it, the first 5 or 6 years was work that Martin actually was able to initiate and run on his own, and subsequently had secured funding from the Australian Research Council for 30 years or so of research. We heard all about that yesterday, and the last few years and into the future, the funding has been secured through ARENA. As a result of that, I was going to put a number in there about how many PhD graduates, and I haven't got that number yet. I understand from Martin yesterday that he has 60 of his own, but of course, clearly the school has more than the graduates that were graduated under Martin's supervision. There's also there's strong alumni that the university's generated. You've all seen the picture that was some 30 years ago. That photo was taken of the crew that first produced the first 20% solar cell. Importantly, I think it's useful to reflect on the more recent alumni and graduates, and I think it's a really important output from the university here. That team there has gone on to great things and to leadership in some very significant companies that have made a big impact on solar in Australia. It's really important to reflect on the new graduates who are out there in the Australian workforce, working for companies like First Solar and Lend-Lease, Infigen, and they're actually on the implementation side of solar in Australia now, and I think it's really important to reflect on that as well. This has all been possible because of the sustained investment in funding in the research, and then the ability for collaboration, cross-collaboration and expertise to be shared throughout the school, and now with the ACAP funding across all the various institutes in Australia, which I think has been really important. I won't go through all that in detail. Suffice to say, I will point out, so the ACAP funding for the UNSW node supports facilities development here in the school and research. It supports about 10 full-time equivalent positions. That's actually spread out over about 30 people, that funding. And those people are working variously in facilities and infrastructure, maintaining the great capabilities that are here, as well as in developing new technologies, new ideas, pre-commercial research, and supporting around 120 PhD students, which is a really significant activity. And importantly, this is a separate funding, but it's one of the clearly focuses here is to make sure that the research is manufacturing oriented. So there's the facility up the road, which I hope you will get a chance to see at some stage, which is the Solar Industrial Research Facility. That funding is the ACAP funding for the UNSW node covers all the programs within the ACAP, all the projects within the ACAP program. In the silicon solar cell activity, there's work under another arena program on hydrogenation, which is looking at materials improvements, and Brett Hallam will talk tomorrow, or he has a poster tomorrow, talking about taking the learning from that other program and developing new concepts for using the same technology. In this case, he's talking about using HIT cell technology to extract even greater benefits. He's also been working the last year in developing the processing techniques to demonstrate the performance from these solar cells, and he's getting for the solar grade silicon efficiencies around 19%, which is in line with the targets for this year. There's also under this program is the silicon tandem technologies, which is intended to access the longer wavelengths where silicon doesn't absorb so effectively. And those structures are these fairly complex structures where you build another junction on top of the silicon solar cell to access these longer wavelengths. There's work going to be reported in the next couple of days by Al Mansouri and by Diaz on the various structures there, where there's clever interfacial layers developed to manage the stresses between the different materials to make sure we get the best quality material from the second device. There's the third gen and thin film work, second and third gen work, which the University of New South Wales has a long history in the crystalline silicon on glass, where I have some background, and the hot carrier and quantum dot work, which you'll hear about from Gavin Conabere tomorrow morning. They've made some advances in the understanding of the materials and have produced the first silicon quantum dot tandem structures, which you'll hear about tomorrow. There's the organic PV devices, where they're again looking at materials improvements, the earth-abundant chalcogenites and kesterite work. There's been some great work there with some new benchmarks set in voltage and current and efficiencies in those devices, which you can read about in posters by Yu Feng et al. Tomorrow. And there's the new excitement in perovskites, which there's a new program being developed here at the university, as there has been with across the ACAP spectrum. We've been working with Monash, with materials from there, to assist with the characterization of the perovskite materials. There was a paper produced in Nature this year that co-authored by Martin and Anita Ho to look at the potential for the perovskite materials. And in this illustration on the right, you can see that there's modelling being done around around the structures for the ideal combination of silicon and perovskite, in the same manner that Andrew Blakers was discussing earlier about optimising the lost absorption within silicon when you put a top layer on top, and making sure that you get the balance right with the materials and the efficiencies. There's the work in 1, 2, 3. This is the third program in optics and characterization. There's an overlap there with and work in collaboration with ANU on plasmonics and mapping the space and identifying the optimum structures to try and extract extra efficiency. Most of these in the Advanced PV program, we're actually looking at extending the performance from silicon alone by extracting efficiency, extracting extra current, extra performance from the cells beyond what's capable of silicon. And the plasmonic work is looking at doing that, enhancing absorption. An important feature of the ACAP program, which is really the first milestones are set for 2015, is to actually to look into the manufacturing costs associated with all these new technologies, because we need to make sure that it's really competitive when we do these new developments. We project forward when we'll be manufacturing, how they'll be implemented, what the cost implications will be. And we've been discussing and we're reviewing the actual milestones and targets associated with that program, with this program, because it's a moving target. When we established these goals early on in the piece, the manufacturing cost was relatively high. It's come down much faster than anybody was expecting, including the Sunshot initiative, which was kind of our benchmark. So we're looking at adjusting those now. The Sunshot targets are to reach 50 cents a watt peak by 2020. There are some technologies, some manufacturers who are there already. We're looking at including some of these advances, which will allow us to bring down the balance and systems costs if we can improve efficiencies, which will allow us to have at a cell or a module level slightly higher dollars or cents per watt target. And so we're working with Sunshot Initiative targets and our own to cost the new technology developments that are proposed under the ACAP programs. The other activity that UNSW is quite active is in the education, training and outreach, and I reference here the work that Alison Lennon was described earlier with the Advanced Photovoltaic Manufacturing course, which will be run in January and February. And then there's the knowledge sharing programs in the conferences like this one and the APVI conference, which ACAP was a supporter of, as well as ARENA. There's the various collaborations within the ACAP family, which I'd like to think we can continue to develop and strengthen over the next years. The perovskite work clearly is an opportunity for everybody to actually develop those skills together, because everybody brings to the program different skill sets. And there's one of the other outreach programs that we do is the virtual production line analysis, and you'll hear about that a little bit later today too from Malcolm Abbott. The collaboration, as my understanding of what UNSW is doing at the moment, and I may well have missed some, and please forgive me if I've missed anybody by name or activity through the course of this, and feel free to come and tell me, because the more I learn, the faster I learn, the better. We're working with ANU on the light trapping and solar grade silicon work, and with Monash and perovskites we work in the teaching program with QESST. And with NREL, we're starting on costing studies, and Andrew mentioned the economic modelling that he's doing as well. I think we'll look to advance that together. Importantly, a lot of the activities here at UNSW are funded by programs outside ACAP, but they leverage the benefits that come from the ACAP relationship. I reference here the 40.4% concentrating cell efficiency record that was announced this week. That was in a separately funded program, another ARENA funded program, but it was improved on, and the results were achieved partly through the ACAP activity, because it allowed the relationship with NREL and the work that was done with Keith Emery over the time that he was able to put into the project was accessed through the ACAP program. So that's where there's an indication of how the different programs interact. There's also the 3.5 Tandem work that's done with Ohio State University. So the 2014 highlights were to establish and improve on the baseline processes for for cell processing because the Tyree building has been re-established, or the work has been re-established in the Tyree building over the last year. So we're now able to get the 19-20% efficiencies on the standard commercial grade silicon that we're targeting getting. We set performance benchmarks in the CZTS material, established the 40.4% concentrating module, and achieved advances in the understanding of plasmonics and hot carrier cells, which you'll hear about from Gavin tomorrow. There's been a lot of excitement, as you know, in the perovskites. The paper released in Nature, we're collaborating with Monash, and that's all enabled by this special research initiative, the funding of the capabilities here at the university, and the collaboration itself. And it was mentioned earlier, but the fact that ACAP has provides the capacity to generate pre-commercial research and allows us to develop these activities. Plus there's the new teaching programs. For 2015, the milestones recorded are that to get the second generation cell efficiencies to 8%, the solar silicon to 19%, and the rear contact tandems rear contacts to 24%. And I don't have a tandem efficiency there. Well, it's on the next page perhaps, we'll check. And to demonstrate a cost advantage of 5% over the Sunshot Initiative's targets. The UNSW activity will do that by looking at advancing materials and device development, the same sort of strategies that were talked about with ANU and Melbourne and Monash and CSIRO, and to resource the activities under and around the perovskites. We'll be resourcing and advances in the PowerCube project, which is what gave us the 40.4% result, to target a 42% efficiency in the concentrating solar cell work. We'll develop the costing models with our partners and the various processes that are being considered by ACAP, so that will be across the ACAP activity, and we'll extend the knowledge sharing activities within ACAP. This is the milestone tables as documented, and there's some indication there of how we might resource all those activities. The costing is added at the end because it'll be based, the costing we do will be based on the developments that are demonstrated over the course of the year. The improvements, we've got to go from 17 in this case to these targets here, and that'll be done through materials and device developments. The same sort of, I'll have a look. We'll work with NREL on the costing targets. If I look down here. And yeah, we'll continue to work on the optical enhancements through light trapping, through materials enhancements, and through device design improvements. It's very general. Oops. So, and this, we have to acknowledge ARENA for its support of this program. Thank you.